Welcome to the first of my courses on statistics, Key Statistical Concepts 1. My name is John Varlow, and I've been training staff within the NHS and academia in statistics, analysis and research methods for over 20 years. The course you're about to take has, until now, been delivered face-to-face in a classroom setting, so I hope it's as interesting to you as an online version. So let's look at the aims of the session. This training is broken down into a number of short videos, questions and exercises, but the overall aims of the session are given here. To start with, it's worth saying that this session has been split into two broad categories, descriptive and inferential statistics. Now I'm sure you've heard these words before, and in the next slide I'll define these categories in more detail. For the moment though, we can think of descriptive statistics as describing the data in front of us, and inferential statistics as making a best guess about a bigger population from the data that we have. So the first half of this training is looking at descriptive statistics. We're going to start from first principles by defining the type of data that we have. Then we'll look at measures of central tendency or middleness. You might remember some of this from school, looking at modes, means and medians. Once we know our data type and typical value, we'll discuss measures of dispersion or measures of spread. And again, you'll remember some of this from school. We'll also look at other simple summary measures like rates and discuss the two most common types of rates, prevalence and incidence. After that, we'll talk about the pieces of data that you have that look a bit strange, or what we call outliers. And we'll talk about some of the methods to handle these. And then finally in our descriptive section, we'll look at how data is distributed, although we will concentrate on one particular distribution, the normal distribution. The second half of the training looks at inferential statistics and starts by discussing what statistical tests you might apply to your data. Now some of these you'll have heard of before, and while we don't go into detail on the formulae, we will look at an easy way of picking the right test for the data you have. We'll also look at statistical confidence, and specifically something called the central limit theorem. This enables us to define something called standard error or sampling error, and helps us calculate p-values and confidence limits. Now we often use statistics to compare different populations, but it's often the structure of populations that's creating the difference rather than anything else. So we'll discuss standardization methods, which aim to remove the effect of different populations' makeup so that we can compare populations more usefully. And then to round it all off, we'll look at measures of association between variables and how this might be shown visually. We'll look at scatter plots and how they're used, measures of correlation, the line of best fit, which again you might also remember from school, and the principle of cause and effect. So that's the overview. There's a lot to get through, but we'll go from first principles and in a logical order that will hopefully make learning these concepts easy. So put on your statistical hats and let's get started. Now, as I said in the previous slide, we need to start with some simple definitions. When I was giving the overview, I said that descriptive statistics were used to describe the data that you have in front of you. To be a bit more detailed, descriptive statistics are designed to describe characteristics of a sample of data. Now this might be the most commonly occurring value, the middle value, or the typical value. Descriptive statistics may describe how the sample data you have is spread, or how it's distributed. What we mean by that is, what shape does it most resemble when plotted? The key thing about descriptive data is that it is definite. There's no doubt associated with any of your measures as you're fully aware of the data that you're describing. If I were to ask you to describe your house, the answer that you gave would be based on your house, not anyone else's. It wouldn't make assumptions about other houses or other areas. but would simply be a factual description of where you live. In the same way, describing data is factual, doesn't make assumptions, and doesn't have anything to do with any other data. Inferential statistics, on the other hand, treat the sample of data in front of you in a very different way. Instead of describing factually the data that you have, you're instead using it to infer or imply something about similar data, usually from a bigger population. As an example, if you were to infer information from the description of your house, you might assume that all houses had a garden, or all houses had a garage, because that's what your house has. You might think that other houses were as big or as small as yours, that they were worth a similar amount, that they had the same number of rooms. We could go on. The thing about these assumptions is that they may be right, but they may be wrong. We're no longer dealing in facts, but in inference. And this is what we do with inferential statistics. We infer something about a bigger population, but there is a possibility that we might not be quite right in our data assumptions. Now, getting the difference between these two types of statistics clear in your head is really important, as our understanding of statistics and what weight we put on them is based on this distinction. Before we start delving into the detail of our data, I would also like us to stop for a minute and think about what we're doing, which is really good practice when doing data analysis. I'm sure all of you will be familiar with the man in this photograph. His name's Albert Einstein, and he was probably one of the most intelligent men that ever lived. He discovered many things and made loads of scientific theories, most of which have stood the test of time. And there is a relativity joke in there somewhere. Now, I've given you a quote here that is accredited to Einstein that's worth considering before we go any further. Now, in reality, I don't think Einstein did actually say this, and it was probably Disraeli or Mark Twain or someone similar. But it is a clever quote, and Einstein was a clever man, so let's do some dubious association and put them both together. And if you want to know more about dubious associations, we'll be looking at this a little bit later when discussing relationships between variables. Now, the quote says, "Not everything that counts can be counted, and not everything that can be counted counts." Yes, it's a bit of a tongue twister, and not one to say after a few drinks, but it holds some deep truth. In essence, it's saying, some things are important, but you can't count them. And you can also count things that just aren't important. For you, as a data analyst, a researcher, a statistician, or just someone interested in numbers, it's tempting to do something with data just because we have it. The modern world is awash with data. What we described as big data just a few years ago is now the norm. And the temptation is to assume that the data is telling us something, and that the more data we have, the less there is that's unknown. But this quote makes the point that there are many important things that you can't measure with data, or certainly not by counting. Data, or numbers, might count the what, but it can never tell you the why. We often refer to statistics as quantitative analysis because it's based on quantity. How much of something do we have? But quantitative data cannot give you the reason behind the data, or how people experience things. This is a realm of qualitative analysis, and it's not dependent on counting things, or on quantity. So, not everything it counts can be counted. And then, of course, the flip side is that everything can have a number associated with it, and we assume that it's important and needs analysing. We've moved as a society to real-time data, And all this real-time data flowing across the system costs a substantial amount of money. But if the conclusions from real-time data are no different than data that is collected less often and costs much less, then there's no point in collecting it. Similarly, if various characteristics don't change, then repeatedly counting will give no extra information. So keep this quote in the back of your mind as we progress through this course, because in essence, data analysis and statistics is about counting. Not everything that counts can be counted, and not everything that can be counted counts. Now, before we get into the session in detail, let's start with a quick quiz on what we've discussed so far.